aspects of autonomous underwater vehicle and its navigation and control problem, and adaptive control of autonomous underwater vehicle, path following control and formation control, and some conclusions. So, the 71% of the Earth's surface is covered by water, and 37% of the population live in 100 kilometers from the coast, and therefore these oceans are a source of food and resources and play an important role in the climate as well. So there is a lot of opportunity to study the physical, chemical, biological and geological phenomena that occur in the ocean and its frontiers with the atmosphere and the Earth's interior. So the research that is very challenging today is on underwater vehicle for oceanic exploration. So this is a scientific challenge. So that is addressed by marine vehicles, and we may note that a single autonomous or marine robotic vehicle may be not adequate to be deployed for a task that is not possible with one vehicle. Rather, you can deploy a group of marine robotic vehicles for accomplishing a cooperative control task, so that the navigation and control of such kind of robots is a challenging task to have this oceanic exploration. So the classical method to explore the oceanic environment, the first one I display here is a vessel, marine vessel. So this marine vessel is okay with some excellence towards the exploration activity, but it has poor maneuverability, and the three-dimensional coverage and time coverage is also not that impressive. Also, it involves high operational costs. On the other hand, we could deploy a diver for such activity, the exploration activities. But what happens is that it may be restricted coverage area, so a diver may not be able to cover a large area, and sometimes it may become dangerous, or it may be hard for the collecting the georeference data as well. So therefore, after these kind of vessels or the divers, the thrust has given to design remotely operated vehicles where the umbilical cord is a link to control the autonomous underwater vehicle, or rather the vehicle, remotely operated vehicle. But gradually it was felt that to make it autonomous, we need to use the computing, control and all sensor technology, so that this underwater vehicle could be deployed in the oceanic environment for the exploration. And it is observed that these kind of autonomous underwater vehicle have high maneuverability, and good autonomy is established to accomplish automatic execution of tedious tasks. And the marine vehicles, if you look at it, they could start from the marine craft, which are very small ships or submersibles, and vehicles that do not travel on the land. They are only restricted to the oceanic environment, and they are called crafts. So the vessel is basically a hollow structure that is made to float upon the water for the purpose of transportation and navigation. And on that, it is larger than a rowboat. So the words vessel, ship or boat are often interchangeably used. In a ship and a boat are basically different in terms of their size, and by virtue of following definitions as mentioned in the Encyclopedia Britannica. So that is one, the ship. The ship is basically a large floating vessel that is capable of crossing open waters as opposed to a boat, and basically it covers um, more than 500 tons of displacement, whereas a submarine, that is any naval vessel that is capable of propelling itself beneath the water as well as on the water surface itself. And the underwater vehicle is a small vehicle that is capable of propelling itself beneath the water surface as well as on the water surface. This includes unmanned underwater vehicles or UUV, or remotely operated vehicle or called ROV, and autonomous underwater vehicle called AUV. So basically we have three vessel, the marine vessel or marine vehicles. One is the ship, the submarine, and the underwater vehicles. Now the problem before us in this underwater robotics is that the first problem is, what force should I apply to achieve the desired speed? That is what the control problem before us. And the second problem before us is the guidance. That means, how should I steer to follow the desired path? And next, what path should I follow? That is the path planning. And where are the ampara? So where is the mapping? Means you want to find out the sea floor, these aquatic animals there. You want to map the sea floor. And where am I in the motion, the navigation problem. So these are some of the problems that we are encountered while the problem with the underwater robotics is concerned. Now, one of the very interesting problem is called SLAM, that is simultaneous localization and mapping problem, where the objective is to design the localization algorithm so that we will take care of the robot pose, and through the mapping algorithm you can map the sea floor, and of course you take the different environments, like maybe either you can get all these inside the sea, what is there and how to make them mapped by virtue of the localization algorithm. And the navigation problem is basically concerned with estimating position, orientation, and velocity of a vehicle. And we have the origin, and we have basically the like origin at the Earth surface. So we have the same origin n rotated with respect to the Zn. So either maybe with the North Pole or the South Pole to avoid the singularity problem. And the vehicle attached frame is B. So we use different frames for defining the navigation problem. The inertial navigation system, or what is called INS, is a very much popular sensor that is used in the navigation problem. And these sensors are used for navigation, and these INS are three accelerometer are used for linear motion estimation in the navigation problem, and maybe three gyros are used for the angular motion estimation. But these sensors are very expensive and they require accurate calibration. So there could be some drift in the position estimate over the time. So to measure acceleration, angular velocity, and compute the linear velocity and position and attitude, this is what we are doing with respect to the navigation problem. And these are the two figures that show that envisage that the earlier one and is the new one in the INS, where no rotating part is here. We have all these gyro etc. there, so that helps to find out the information that is needed for the navigation problem. These position, orientation information, velocity information, all these are obtained through this INS. So the motion control problem of the autonomous underwater vehicle is as follows. So we have the ship or the vehicle or the autonomous underwater vehicle. So we use a compass or a gyro and measure the yaw yaw angle and yaw velocity, and sometimes we may use the observer to estimate the wave, some disturbances, and then the pilot gives some kind of reference input, that is for the path planning, or maybe the navigation problem, the desired orientation, etc. Then you design the control here, and of course all the objective here is to steer the autonomous vehicle in the desired yeah undesired yaw rate, when there is a wind disturbance is there, or oceanic disturbance is there. So the objective is to achieve the right or the desired angle and velocity in presence of all these disturbances. So this navigation and control problem, the guidance problem, we have the weather station that gives the weather data, and we define some waypoints, and then by virtue of a trajectory generator, we get the guidance, time. Then we have the most the control system design that takes care of the waves, the disturbance in the waves, or oceanic currents, or wind velocity, or that is the resistance, and maybe we can estimate the position and velocities by some observers. We can use some sensors like gyro, compass, etc. The objective is to control these marine craft or the autonomous underwater vehicle to accomplish the desired motion control in presence of all these waves, wind and ocean currents. So we have two things here. One is the ROV, the other is the AUV. So ROVs are low speed box vehicles, and they are strongly coupled dynamic and the nonlinear model based control are required for dynamic position task, and where these are fully actuated. That means the number of degrees of freedom to control is either equal or more, or less, not more, less than the actuating signals. That means more number of or at least the number of degrees of freedom is equal to number of actuators. So no freedom is left unattended. But on the other hand, in case of autonomous underwater vehicle, these are high-speed vehicles. We consider many times the decoupled dynamics, and we can use the gain schedule controllers, where we predetermine the gains and then use them for the control of the motion. And these are basically under-actuated. That means the number of degrees of freedom is always more than the number of actuation points, actuators. So therefore these ROVs are suitable for station keeping, which are basically low speed positioning systems, and whereas the AUVs are intended for high speed maneuvering. And this guidance control law, that is primarily to steer the vehicle so that it will orient towards the desired angle. So objective here is that to drive the orientation error, that is the difference between the desired and the actual, to zero. So this is the typical AUV structure. It is a has a nose kind of structure here, and is the tail, and the middle portion is the hull. And we have thruster, we have the stern, and we have the rudder. So these are the actuating devices that are used to drive the AUV to control the motion. And as I told you that the challenge before us is to control the AUV to accomplish the desired motion plan. So but to do that, we have certain uncertainties, as you see. That means the ocean current is there, and added mass is there, or there could be disturbances, or there could be uncertainties in the dynamics of the underwater vehicle. So all these necessitate to design adaptive controller to get the appropriate control, motion control, objectives. So adaptive control, as you know, it needs a model structure. You have to define a model and you have to estimate its parameters. Once you define a model structure and estimate its parameters, then what happens if any change in the dynamics happens, the model parameters will change. As a matter of fact, the model will change, and in accordance with this change, you can design a controller that whose gains are adapted with respect to the changes that happen in the dynamics. So therefore, this adaptive controller is a class of controller where depending upon the changes in the dynamics, the controller gains are changed, and uh, there are different adaptive controllers, but the one I am interested to discuss here is the self-tuning controller, where the each sampling time the model is estimated, the model is identified, and therefore the in case of the uncertainties you can achieve the desired performance. So here the parameter estimation is used in real time to estimate the parameters of the AUV or the system or the plant. And this is the adaptive control where we can have either, so the plant is here, the AUV is here, and we have the parameters, plant parameters are estimated, and these plant parameters are then used to design the controller. So this is the model reference kind of controller, and this is basically we are using a performance index. So that means if the performance index is not met, so we have to tune it. So there are adjustable parameter of the controller, so that can be adjusted so that the control action U can vary adaptively, so that the plant gets the appropriate control action, so that the output of the plant follows the reference signal. So this is the direct and indirect adaptive controller, in which we have in the direct adaptive controller, we directly estimate the plant parameters, and then the plant parameters are parameterized in terms of control parameters, and they are estimated through any identification algorithm, and then we design these estimated control parameters are used to design the controller. But on the other hand, in a adaptive indirect adaptive controller, we have the plant and we have the plant model. We estimate the plant parameters, and those plant parameters are used to design the control parameters, and thereby you get the adjustable parameters of the controller. So this is called the adaptive controller in the indirect way of tuning the or designing the control law. And there are different adaptive controls available. We have self-tuning control, model reference adaptive control, variable structure control, and we have the direct identification or indirect identification, and STS means self-tuning control, and we have the model reference adaptive system with parameter setting, model reference adaptive system with the signal setting, and we have heuristic controllers are also there for the adaptive control domain. So these adaptive controllers, one of these adaptive controller is a self-tuning controller that is being used here for the autonomous on-road vehicle that I will be discussing. And this book, this is a book edited by me and my friend Sanjay Sharma, and that is published by the IIT. So that is a navigation and control of autonomous marine vehicles that covers a lot of control of these autonomous underwater vehicles. So one such technique I will tell you today, that is the Narmax self-tuning controller. Narmax means nonlinear autoregressive moving average model. So what is the problem for us is that we have the desired path, and the AUV is to follow this desired path. So the controller updates the path parameters of every instant, and then it provides the appropriate control to this AUV, so that the desired path is being tracked. So for this path following control, there are certain control issues like uncertainties in the AUV dynamics, and there are disturbances because of these wave ocean current or sea waves, or that the data rate, the oceanic data medium, the data rate could be very low, so or there could be payload variation. So in face of all these uncertainties, the challenge for us is to design an adaptive controller such that we are able to follow this path accurately. So therefore, the objective here is to develop a nonlinear, autoregressive, moving average exogenous model of the underwater vehicle, and then to define the waypoints and line of sight guidance control law for tracking this desired path. Then design a self-tuning controller for heading and diagonal, and then simulation of this proposed controller and implementing the same in real time. So this work, the details are available in our paper IIT International Control System Technology 2017. So before going to design the controller, let me tell you the AUV kinematics and dynamics. So here there are 6 degrees of freedom of the AUV: the source, roll, eve, yaw, pitch, and sway. So where the x, y, z and p, q, r are basically the linear position and velocity. These are the angular position and angular velocities. And the linear and angular motion are basically, there are two frames. One is the inertia frame and the body frame. So then these vectors like eta 1, eta 2 are basically the linear and angular motion. Okay, and this is the linear and angular velocity. This beta 2 is the linear and angular velocity. Okay, this the v1, v2 are linear, and v1 and v2 are linear and angular velocity with respect to the body fixed frame. So what we do here, we develop a Narmax model for the AUV. So here you see, this is the real or the hardware AUV, and we give some kind of input here and find out what is the output YP. And these are the tab delays. Z-1 is the one sample delay. So the previous instant values and the previous control values is the X. This is what is the X. And then our objective is to extract this linear relation and nonlinear relationship F, that is between these past values of input and output, or U and Y. So that will eventually you get this model identified. And this difference between the actual output and the estimated output is E, and that E need to be minimized in order to identify the dynamics accurately. So we developed two models, Narmax model, one for the heading motion that involves the sway motion and the yaw motion, that is V and R, V dot and R dot. And then we have the depth motion, that is W dot and Q dot. That is pitch is Q and heave is basically W. So and these are the this is the heading motion Narmax model, where VK and RK are the the outputs, and the previous values are VK minus 1 and RK minus 1, and these are basically the functions, and delta R is the basically the rudder input, and this is the error signal. So F1 can be written as different different constants and the previous values of VK minus 1, RK minus 1, and so on and so forth. And G11 is basically alpha phi 1, and G21 is beta phi 1. So similarly, the Narmax model for depth motion we can find out. We can represent it as W and Q for kth instant, which is a function of the past values of W and Q, the output, and then the input, the storm input delta S, and the error signal. And these are the representation, that is different constants, alpha 02 to alpha 42 and beta 022, beta 42, and this is alpha 52 and alpha beta 5. So the path following control problem, what we do, we define some waypoints let us say waypoint 1 x1 y1, waypoint 2 x2 y2, and waypoint 3, like so different waypoints, and this is the region of acceptance. So what you do is we then design a line of guidance strategy in which the waypoint, the previous waypoint, the current waypoint is connected by a rectilinear path, and this is the actual path. And this waypoint tracking using the line of sight guidance law, what we do is we want to follow this desired the path while avoiding these obstacles, so that the starting point and the goal, so the that can be reached in this path, following this path. The Narmax model-based self-tuning adaptive controller that we are designing here, we have for two motion. One is the heading motion that involves three variables, the V, R, and DR, where V and R are the V and R are the the angular velocity and position, and delta T the thrust or force or torque, and similarly W, Q, and LS is for the diving motion. So what you do is we take the Narmax model structure, then you take these input and output to identify the parameters of the AUV, and those parameters are used to design the dynamic controller, which are the two gains K1 and K2, and then we have the desired line of sight path, and we want to accomplish this, so by virtue of this controller. So what we do, we have two models, Narmax model, one for the heading motion, the other for the diving motion. I equal to 1 is for heading motion, I equal to 2 for the diving motion. And the output, that is in this case, the previous case, that is the output for the heading and output for the diving in general, we can write as y equal to phi transpose delta I. So we use a recursive least square estimation technique to estimate the parameters of this Narmax model. So this is the recursive extended least square estimation algorithm that identifies the parameters of the Narmax model, where the theta I hat is the current estimate, theta I hat k minus 1 is the previous estimate, and S is the covariance matrix, and lambda is the forgetting factor, to give the more weightage the current information. So we introduce a forgetting factor, and this epsilon I represents the residual output error. So what we do is we design a kinematic controller where the objective function V1 is for the AUV kinematic is chosen as V1 half into EK transpose R. R is a matrix which is positive definite, and we have the error, and Q is a positive definite matrix, and the error vector is E heading and in the diving motion, and the error objective function V1 then we represent in this form, and then we also calculate the cross stack error. That means this is the I minus 1th waypoint and ith waypoint, we connect them with a rectilinear path, and these are the different region of acceptance where dk the error is less than 0, more than 0, and equal to, so if it goes across the path then the error is 0. So then we define this cross stack error. Dk is the path parameter, A is the path parameter, and xk is basically xk minus x0 is basically xk, yk, zk minus the initial values x0, y0, z0. And C has two components, C1 and C2. So X0 and C are basically the offset from the desired path, and dk is defined as this dk is defined as the y error and z error at kth instant. It's called the cross stack error along the heading and diving motion. So we design a dynamic controller for which the rudder plane input are the torque and the stern plane. These are the constants, and these are the errors R and Q. So these errors RE and QE are represented by these dynamics, and similarly we define the objective function V2 in this manner, the positive definite. So this, then you substitute these values, then you get V2 like this. So now the net error objective function is the kinematic controller and the dynamic controller. So it can be minimized in presence of actuation constraint, and where we formulate as the cost function as half x transpose qx plus c transpose x plus cf, where your x is like r, q and these constants. So the objective here is that to minimize this cost function subject to these constants. So these are the constants, like these are the for XR, this is for the gain, and this is for the Q, and this is for the second constant of the controller. So we implemented this controller for in real time. For that, we realized a underwater vehicle. So this is the picture of the autonomous underwater vehicle, and here what we did is we put the depth sensor here, and this is the Atmega 2560 for the data acquisition system. This is the single board computer where the control algorithm is downloaded, and this is the INS, and this is the SCDC. This is basically the ocean server make battery and management unit and ACDC converter. Sorry, DC-DC converter. And this is the lithium ion battery, and so this is the way we fabricate this AUV in the laboratory. Now, while implementing this controller, we have taken three units. One is the sensor unit, computational unit, and actuation unit. In the sensor unit, we have different sensors. The Doppler velocity log, we have the GPS, we have the depth sensor, so they may give you the UV, XY, and Z. And similarly, we have INS that gives you the PQR and these error signals. So then all of these signals, the sensor signals, are then combined or maybe used in the sensor fusion by Kalman filtering algorithm. And we have two models, one for the diving motion, the other for the heading motion. These are the inputs, and this is the output from these. So basically these are the input and these are the outputs. So these input output information is used to identify the model parameters, and then we design two controllers, one the kinematic controller and dynamic controller. And as I told you earlier, that the objective is that we use an online optimization algorithm and then estimate the gains Kp and Kp considering the actuator saturation. And then we have our Linux operating system and robot operating system, and this optimization is done by Mosaic toolbox. And all of these this computational unit, it gives us the two things, like it gives the input to this PWM generation, that the dynamic controller input goes to the PWM generation block, that gives you the different control inputs to thruster, rudder, and stop. These are the three actuators, and we have considered a desired heading for 0 to 5 second is 0, 5 to 20 second is 1.57. This is the oriented desired heading, and 20 to 35 it is 0, and 35 to 50 it is minus 1.57, and 50 to 65 it is 0, and 65 to 75 it is 1.57. So what we have chosen the initial state of the AUV as all 0, and then we pursued the simulation for 800 seconds with sampling time of 0.5 second. We define the saturation, actuator saturation, that R is less than equal to 1 and Q is less than 1, and these two gains are less than 0.6 each. So we use a robot operating system and define different tasks, and to integrate the sensor fusion, like we have the different velocity, angular rudder angular acceleration, joint states. Then we measure all the variables and integrate them by using the robot operating system. Then this is the result that we obtain through experiment, that this dotted line is the desired heading. This is basically the blue line is the actual heading. So the heading error, so it goes to 0 with the time, and this is the estimation accuracy. The estimated velocity is the dotted one, and the blue line is for the actual velocity. So the estimation is good, and the parameter estimated, this is the plot that shows the different parameters like beta 0 to beta 4 with respect to time. So how they are updated with when the control, and the tracking of desired heading by the prototype AUV. We see here the rudder orientation. This rudder orientation delta R, and similarly the computational activity, the two computation time we noted. One is for identification, and this is for the control computation. So we compare the computational time with respect to the controller, simple self-tuning PID controller, and the controller that we have now discussed. We could see that the self-tuning adaptive controller takes 0.11 second. Although it successfully tracks the reference path, the state and actuator constants are not taken into account here. While the second case, we have the self-tuning adaptive controller, it takes 0.8 second. The computational time is more as compared to the previous controller, but it considers both the state and actuator constants. Okay, so, let me show a uh, so this is the we tested in a swimming pool. Yeah, this is the heading heading motion. Okay, and the second one is basically the diving motion. Okay, so this is what we have accomplished in the real-time verification, and but this is the one I have described to you, is the path following control problem where only one AUV is put to the task. But there may be necessity of deploying more than one AUV for a group task to have a cooperative control motion. So therefore that is called formation control. What is formation control? Is basically, if you look at the sky in the evening, a group of birds are coming to their nest, and they are following a pattern. That pattern is the formation. So here is the leader, and rest are following the followers. So the flocking of bird, if you mark carefully, this is a formation. And similarly, if you see the fishes in the pond or somewhere, they are also following a group motion. Some of the fishes is the the leader and rest are the followers. So this nature-driven formation gives you the inspiration to design a cooperative motion control for autonomous underwater vehicles. That's what is the next agenda. So we design formation control for coordinated control of a group of unmanned autonomous vehicles, the motion in the formation. So the number of different sensors can be included here. They are distributed on multiple AUVs. In case of any AUV of the fleet breaks down, the chances of mission failure can be reduced. And this is used for surveying a large area. But there are certain challenges here like collision avoidance, because if they are in group, if other AUV, also the follower AUV or with respect to leader AUV may be considered as an obstacle. So the obstacle avoidance is a great challenge here. And formation maintenance, how to maintain the formation all the time, and inter-vehicular underwater communication. We need to establish a good communication between different AUVs for this formation control. And the formation control we can design using several techniques or approaches. One is the behavior-based approach, synchronization-based approach, virtual structure approach, or leader-follower approach. In the behavior-based approach, based on the sensor input, a control input is generated to achieve a desired behavior response like collision avoidance, obstacle avoidance, formation keeping, and goal keeping. So this is the obstacle, and we have the different AUVs. So we need to design a formation control or the cooperative control such that the collision and obstacle could be avoided, so that while maintaining the formation to reach the goal. So this is the virtual structure approach, where synchronization based and virtual structure approach. All the AUVs in the group are assigned a particular path based on desired formation, and control is developed for achieving the desired velocity. Here the objective is to achieve the desired velocity, not the desired position. And these are the individual path you design, not a common task. The desired dynamics of the virtual structure is defined. The desired motion of the virtual structure is translated into desired motions for each agent. Individual tracking controllers are designed. Here each of the AUV is considered to be an agent. So like you see, this is called multi-agent approach. That means any of the bird, so it is considered as an agent. So this multi-agent based control, where individual vehicle is considered an agent, and therefore the communication between these agents can be represented by a graph, and thereby we can use the graph theory to design a controller based on this multi-agent approach. So this is the leader-follower approach, where the path is defined to the leader, and there will be the followers are communicating each other. The followers communicate in between. Not all the followers are communicated. So depending upon the communication, you can have your graph, and then from the graph you want to design a controller that is called consensus-based control. So that means all the agents should reach to a consensus or maybe a desired value, so to achieve this leader-follower group motion. And there are some conclusion of this work. So to capture the unknown dynamics, or rather in case of uncertainties, we can design a adaptive controller, and here we have chosen a NARMAX, the non-linear autoregressive moving average exogenous model structure, and we have used the recursive extended least square algorithm to estimate the parameters of this model. We have also we have developed a self-tuning controller and implemented through the line of guidance control law, and the actuation signals are generated while considering the actuator constraints for practical feasibility of implementation of this algorithm. And effectiveness of this control algorithm we verified both in simulation as well as experimental environment. And these are some of the publications that arose from this paper, and these are some of my students, Raut, Sahu, and Roth, and then Zhuang and Chavi. So I must thank them for doing this work, and which I'm presenting here. for the control of autonomous underwater vehicle. Thank you. So any question, if you wish to ask me, please do so.
Thank you very much, sir, for this wonderful session. Audience, please, if you have any queries, you can unmute yourself and directly interact with sir. I thank you all for being late this evening. Anyone? Anything?
Hello, sir.
Yes, please.
This is Ravi Shankar, sir. I have two questions. The first one is how you obtain the model of the vehicle, and second thing is how you validated this model.
Yeah, very good question. Actually, you see, no matter whatever your understanding on the dynamics of the AUV, but we end up with a fixed dynamics. Therefore, when there are these uncertainties, we are not able to control appropriately. So therefore, at every sampling time, every iteration, you must estimate the parameters and thereby identify the dynamics. So for that, what we adopted is that we pursued a system identification in which we have done two things. One, we have chosen a model structure called Narmax model structure for heading and diving motion. And then we employed a estimation algorithm to estimate these parameters. So this is the recursive least square estimation. And what we do is we have represented the dynamics in these two. There are two models. One for the heading dynamics, this model. Another is for the depth model, this dynamics. So these are the coefficients, alphas and betas. So these are estimated by using this RLDS algorithm. And once you estimate at every, so let us imagine at k equal to 0, you give this input and output and estimate these parameters. These are used to design the controller. This is how we proceed. Okay. And regarding the validation, yes, the validation is basically the convergence of the parameters. You see the convergence. Yeah, these parameters are converging and this estimation. These are these bottom two figures is for validation. Okay.
Okay, thank you, sir. Actually, I'm working on the same area, sir, and I'm referring almost all your papers.
Okay, that's great. Very good. What is your name, please?
Sir, it's Ravi Shankar Desai from BITS Pilani, Goa, sir.
BITS Pilani, Goa. Okay,
Yes.
why don't you meet me sometimes?
Yeah. Hello, sir. Pardon.
Why don't you meet me sometimes in IIT Goa?
Okay, sure, sir. Definitely, I'll meet you, sir.
I believe, sir, he was waiting for your lecture. Very eager to listen to you.
Good.
Yes, sir. You're the first one. You're working in same area, and I'm interacting with you, sir.
Okay, that's very nice. And I will be very happy if you can
Yes,
do something good in this area. Very interesting area.
Yes. Okay. Thank you very much, sir.
Yeah.
I believe you are satisfied, Dr. Sai. Dr.
Yes, sir. Yes, sir. Very thankful for you because I'm very
Actually,
eager
the
to.
lecture was not cancelled; it was just postponed. So I informed everything in the WhatsApp group. Probably you have not seen that.
Okay, sir.
Anyway,
Because I'm very eager to listen Subudhi
yeah.
sir's lectures.
Okay, great.
Okay, thank you. And thank you for giving me opportunity, sir.
Okay,
Anyone
thank you.
else?
Okay.
So if there are no further questions, I can conclude the session. So thank you once again, sir, for giving such a wonderful lecture in this RACES 2021 and especially giving your time despite your busy schedule, I just believe you might be having so much work and all. Still, you are, uh, you gave us your valuable time. So thank you, sir, and hope to see you again in near future with some another.
Thank you very much. Thank you.